All right. So I will first introduce Campana points and then tell you some properties, conjectures, and heuristics about them on toric varieties. Today I work only on toric varieties, so let's start by fixing the sum notation. So to define my Campana points, I need three types of ingredients. I need some arithmetic setting. So typically for me, this is fixing a number field. And the ring of integers. But for the purpose of just defining Campana points, we could just think of some Dedekind domain and its fraction field. So in particular, if you want, you can think more in more geometric terms. Instead of K, think of the function field of a smooth affine curve. Say something like spec OK, and then you see the relationship between the two. All right, so we have our arithmetic part of the setting, then we need some geometric parts, some variety to work on. So for me, this will be toric varieties. So X is going to be a smooth, proper toric variety defined over the field that I just fixed. And now we know that toric varieties are defined by some combinatorial data. So it's defined by a fan, sigma. And recall that a fan is a collection of rational polyhedral cones. Such collection is closed undertaking faces of cones and undertaking intersections of cones. And then each of these cones corresponds to an affine open subset of my toric varieties. And the way these affine opens are glued together is prescribed by the fan. So this is the combinatorial data we have. And out of this combinatorial data, we're going to keep our mind fixed on the one-dimensional cones. These are the rays. So sigma of 1 is going to be my set of rays, rho 1 up to rho s. We just give them some names. And for each of these one-dimensional cones, there is an associated toric invariant divisor, which I call the I. The toric invariant divisor on X corresponding to or defined by rho I. And then I'm going to give also some notation to the union of these, the one union to the S. This is the toric boundary of my toric varieties. The complement of this toric boundary is the open torus orbit. Yuri, your microphone is on, I can hear you. All right, so this is the first part, but now I fix both a field and some ring inside of it. So I'm also going to construct a model over this ring. So my curly X is the toric OK scheme, which is defined by the same fan. Sigma. And this is, because of the choice of sigma, this is a smooth, proper model of my variety X over OK. And we're going to work on this model. On this model, we also are going to consider curly DI, which is the closure of the I in the model. Or if you want, this is the toric invariant divisor in the toric OK scheme defined by this fan sigma. And I'm going to also have curly D, which is just the union of the curly Di's. So D1 union up to DS. It's a lot of notation, but this is my geometric part of the setting. And then to define Campana points, I still need some to fix some parameters. So this is the last piece of data. I'm going to fix an S tuple of integers, 1 up to S. And these are positive integers, which I just fixed. And using these integers, I'm going to define another piece of combinatorial data, a divisor dm, which is now the effective divisor sum 1 from 1 to S of 1 minus 1 over mi as coefficient of curly di. And of course, I can do the same by taking the generic fiber. I'm just looking at the same thing over K. All right. So now this divisor is also called the Campana orbifold divisor, or you can recognize it from the rational geometry. It's a divisor with standard coefficients. We are going to define the set of Campana points over OK, so OK Campana points. On the Campana orbifold curly X and curly dm. And the set of Campana points on this orbifold is defined as integral points with special properties with respect to the boundary divisor. So with notation, this is xdm of OK. And precisely, it is defined as the set of OK points. Now, curly X is proper, so OK points are the same as K points on this curly X. And we choose such points, we look at them as integral points, and then we look at the condition for each boundary component, so I from 1 to S. We are going to require that if we look at the pullback of the boundary component di and the dimorphism from spec OK to curly X, which defined my OK point, little x, then this pullback, which is going to be an effective divisor, then I write it down with coefficient over P. Here P runs over, if you want, the primes of my ring OK. And the condition is that the coefficient of each of these components is either 0, or if it is non-zero, then it is at least mi. And this is true for every component P. So for every prime divisor on spec OK. Okay, so what we do, we take every component of the boundary on the variety or the model we chose. We look at the pullback under this map from spec OK to curly X. It's an effective divisor, and we want this effective divisor to have coefficients at least mi. And this has to be true for all coefficients, and then for all boundary components di. Another way to consider this is to look at
Marta, and can I ask,
yeah.
sorry, is it really important that we are considering all our varieties over some ring?
Well, this condition doesn't make sense if you work over a field.
So what are you doing here? So you're taking a point on a toric variety, and then you take a pullback.
I'm taking a point. Something like this. Okay. And here inside I have my divisors. And then, well, there are two possibilities. Either the point is contained inside the divisor, and this is something that I don't want to happen. And or the point is not contained inside the divisor, but it may intersect the divisor at some special points, at some close points of this. This is a Dedekind domain.
And so
and so what I'm asking is that when so if I call this map X, then here I have this pullback. This is an effective divisor. It's not the whole thing. That would happen only if the image of speckle K is contained in DI. And then I'm looking at this. I'm looking at this divisor and looking at these coefficients. So there is a unique representation as a sum of prime divisors. And I'm looking at this coefficient and I'm telling I want this coefficient to be high, which is the same as saying that whenever the image of this map intersects the I at some prime, then this intersection has very high multiplicity.
So there is some tangency to every component of the toric divisor, which it really intersects.
Yeah. So either there is no intersection, and that's fine, but if there is some intersection, then I want my intersection multiplicity to be high, and as high, how much high, that's prescribed by the multiplicity MI that I fix.
And will you illustrate this notion by some example later?
Yes.
Oh, great.
Yes, so what I wanted to write down now was an alternative way to write down this sum. So when we write down this pullback, we can actually write down explicitly what these coefficients AP are. So what we get is a sum over prime divisors, and then here we have that these coefficients are P. So valuations in the discrete valuation ring of this prime divisor P that I fixed of some Fi, and here Fi is a local equation of for di at the point X and inside curly X. Okay, so let's try to see this on an example. Perhaps I can write here. So I'm going to do the easy example, which is the projective space. And if you want, the projective space is given by this fan here. Row 0, row 1, and row 2 are going to be the names of my arrays that corresponds to the coordinates x0, x1, and x2 in the projective space. And then we have that these divisors that we're looking at, the di curly, or even the curly di, these are just asking one of the corresponding coordinate xi is 0. So these are just the three coordinate lines in P2. And okay, so we are trying to look at the Campana conditions. So what happens? We want to do our pullback. In our case, a local equation for di in the integral model of P2, which is just P2 over my base ring. And if you're not familiar with the number fields, perhaps I should have said this before, then you should consider k to be the rational numbers and OK to be just the integers. At some point later in the talk, we will focus on this case only. So what we are asking for here is, let's look at a local equation around my point. So we fix a point, and then a local equation for di is going to be just xi divided by L, where this L here is some linear form, such that L of the fixed point is 1. So we say, we look at the principal open subset of P2 defined by L being non-zero, but if we look as this principal open subset as a subset of P2, say, over Z, if we want the integral point X to be contained in such an open subset, then the condition is really, it has to be one linear form that satisfies this condition. Otherwise, the point is not contained, fully contained in the open subset. So this would be a local equation on such an open subset for my point. And the nice thing that we realize, if we look at this, is that, okay, I'm going to now finish up the example in here. So the set of Campana points on P2 with some parameter M0, M1, M2, say over Z, so that it's simpler to write down. Then it's going to be okay. Yeah. Let's just write it like this. So Z points on P2, in particular x0, x1, and x2 can be chosen to be integers. And to have the possibility that there exists a linear form like this, such that L of x is equal to 1, then it makes sense to assume that x0, x1, and x2 are co-prime. Otherwise, we don't have one such. So the GCD of x0, x1, and x2 as representatives of the point is 1, and we can always find such representatives. And then the condition, the Campana condition, is asking that the p-adic valuation of xi is 0 or at least mi for every I, and for every p, which now is really a prime number.
Sorry, and what's mi in our case?
Mi is fixed.
Yeah, so it's also a part of the data.
It's part of the data, yes. We fix the parameters in order to be able to define Campana points. Are there any more questions about this, the technicalities of this definition?
So, for instance, suppose that so D is some divisor supported on the T invariant. It's some T invariant divisor, right? So, suppose that we choose all mi's to be equal to 1.
Yes, that's my next remark. So we have two things to look at to be able to relate this to what we know. So this is true in the example, but also in general. If we take mi equal to 1 for every I, then what happens is that this divisor dn is 0. We also have that if we look at this condition, we say that the periodic valuation of something is 0 or at least 1. And that's going to be true because this something has a periodic valuation at least 0, being an integer, and the same also in the general case. So in particular, we have no condition So in this case, we have the set of rational points. Which is the same as the set of integral points without any conditions with respect to the boundary. And this is because I chose my model to be proper, so I can do it. So mi equal to 1 gives no condition. And the other extreme case is, well, what happens? So if I increase my mi, I get smaller and smaller sets. I get more and more restrictive conditions. What happens if I take the intersection of all such conditions? So I take Campana points with respect to m, and I intersect for all possible parameters m. And recall that these m's here are just as tuples of positive integers. So this intersection ends up being the set of integral points in the complement of my divisor D. And why is that true? Because we take my conditions, and the condition is that either it is 0 or it is at least mi. This thing on which we are imposing the condition is an integer, and we ask either 0 or bigger equal than m for every possible positive integer m, which means that the second possibility for this condition cannot be satisfied, and so only the first one can be satisfied. And this part of the condition is just the integrality condition with respect to the given boundary component. So if we intersect all these sets of Campana points for all possible parameters m, what we are left with is the set of integral points, which is contained in each of them. And in our case, because we are working with a toric variety and because of the choice of the boundary that I got, this is not extremely interesting, but okay, it's some set of units. So these are integral points on the torus in this case. So units. All right, so now I'm going to lift these definitions to the universal torsor. First, let's try to analyze this condition a little bit better. Oops. So this condition, the periodic valuation is either 0 or at least mi, means that now we're talking about some integer xi and some prime number p. This condition means that if p divides xi, then p to the mi needs to divide xi. This is what it means. And this is also known in number theory as the definition. We require the integer xi to be mi full. So in order to lift to my favorite torsor, I'm going to recall the Cox ring of a toric variety. So I'm going to find the model of this Cox ring over my ring of integers. And it is just a polynomial ring in S variables where each of the variables corresponds to one of the rays. And then using this Cox ring, I can define a torsor, which for me will be denoted by curly Y. And it is just the spectrum of this Cox ring, so the affine space, A to the S. But not the whole of it, it's an open subset. And the complement is defined by certain monomials depending on the maximal cones. Of my fan. So it's a combinatorial piece of information. And here the notation means that this d sigma is nothing but sum for all the rays that are not in a given cone sigma of the corresponding torus invariant divisor, and y to the d sigma is just some compact notation for the monomial. We take product over all the coordinates, and then the exponent of y rho would be the coefficient of the rho in here. So in this case, it is 1 or 0, 1 if rho does not belong to sigma 1, and 0 if rho belongs to sigma 1. It's not extremely important to know precisely which one this is, but in any case, we do have the example of the projective plane where we do have A3. And then the set that we are removing is just, in this case, V of x0, x1, x2, which is the origin. And this is my torsor. And it has a map down to the original toric variety, in this case, V2. And this is a GM torsor. And in the general case, we have a map from Y to the toric variety, which is a GM to the R torsor, where R is the rank of the Picard group of the toric variety. So I call this torsor morphism pi. And I'm going to tell you what the pre-image of the set of Campana points look like on Y. So points on Y with coordinates y1 up to ys, integral points on Y, that map down to Campana points are precisely those that satisfy the condition yi is mi full for every I. Okay, so let's go back a moment. Here we have this mi fullness condition. So I think that I should have added one thing. So if we require these conditions on the, well, divisibility by primes, let's say, or periodic evaluations for every prime, this is our M fullness condition. Okay, so essentially what we are doing, we are looking at points with coordinates y1 to ys that are integers. The reason being that y is an open subset of some affine space, so the points can really be written very simply as tuples of integers, and then we give some condition to each of these coordinates. So that's a very simple description in the case of toric varieties. And this is my arithmetic condition, if you want. So I'm looking at points on this open subset of my affine space, so my torsor, and I add this arithmetic condition that the points should be should have coordinates mi full for every I. All right, so why do we care about these points? Well, the first reason is what I mentioned before. If we choose our parameters carefully, we can have the whole set of rational points. We take mi equal to 1 for every I. Or if I want to get integral points, I should have to take, let's say, in quotes, mi equal to infinity for every I. I've not written down this precisely, but we think that we can think that taking the intersection of all these sets of Campana points gives us back just a set of integral points. So in a sense, we say Campana points approximate the set of integral points by taking parameters larger and larger. So what I want to do now is to measure these points and give you a conjecture about the distribution of Campana points, which is a generalization of a known conjecture about the distribution of rational points. And in order to measure my points, I have to define heights. So let's see. The first thing, to make notation easier, from now on, we only work with k, the field of rational numbers, and OK, the integers. And I'm going to have to fix a line bundle, and I take an ample line bundle. On my variety X. Now I can use this to define a way to measure my points. So the first observation, I'm working in the setting of toric varieties. My ample line bundle is also very ample because my toric variety is complete and smooth. And I have a precise description of the set of global sections of this actually very ample line bundle, which is generated by some oh, well. How do I write this down for you? So the one thing that we do have is that we can write all our effective divisor linearly equivalent to my L as linear combinations of L sigma, where sigma is a maximal cone. And this gives us a nice set of generators for the sections, global sections of my line bundle. And this These representatives sigma can be written uniquely in terms of the torus invariant divisors. Where here we do have that these L sigmas are the unique represent. Somebody has a microphone on. So these L sigmas are the unique representative in the basis of the Picard group, which is given by the torus invariant divisors, the rho with rho, which is not array of the cone sigma. So every maximal cone of my fan gives us one set of such rays, and they correspond to a basis of the Picard group. Each maximal cone gives a different basis of the Picard group. And this is true because X is a smooth toric variety. Okay, so this L sigma is the unique representation of L in this basis. And all together, they just give me some data, their coefficients, which I'm going to use to define my height. So the height can be written on the torsor or on the toric variety in two ways that are compatible. So on the toric variety, we just look at points, and then we get this linear system, a complete linear system of the line bundle L, and we get mapped to some projective space. And we use this basis of section given by the effective divisors that I just defined. And then on any projective space, we have a standard veil height which we can use by composition to define a height on X. And the height is just submorphism from the set of rational points to the real numbers, with a very nice property that whenever we fix some number here, then we have a finite number of points with height at most the given fixed number. We can write down the height very explicitly on the torsor. So here we have a map, and I'm going to call this one my height, because I'm going to use it later on. It is a map that sends a point to the maximum over all these maximal cones sigma of absolute values of monomials corresponding to these L sigmas. Now this would be just some product over all the coordinates y's and with exponents the coefficients of the divisor that I just defined as sigma. So here we're just taking absolute values as real numbers. Oh, I think that I said that I would work over Z and then I forgot. Okay, so this is Z. And this is Q. So it should be a little bit more clear. We're just looking at integers and then monomials of integers. There are integers again, and we just look at absolute values. Now that we have a height, then I can tell you what we can use it for. We have a conjecture in joint work with Arne Smith, Sho Tanimoto, and Tony Varida Alvarado. We can look at the number of points of bounded height. So this is really the cardinality of the set of points in my torsor, if you want, or downstairs in my on my toric variety. I can do this because this is a 2 to the R2 map. So it's a finite map. So it's a map with, it's a function with finite fibers and all of the same cardinality 2 to the R because of my choice of the base ring set and the fact that I have a GM to the R torsor. So in principle, the conjecture tells me something about the cardinality of points of bounded height on this set, but for simplicity and for the counting that I want to explain later, I'm just working over this torsor. So we just look at points in here. Such that yi is mi full for every I. So this point lies in the preimage of the set of Campana points, and the height of this point is at most b, which is the same as requiring that all of these monomials have absolute value at most b. And then because of how we define the height, I can tell you that this is indeed a finite set. So this cardinality is a number. And what we're going to do is look at what happens to this number when we take the bound to infinity. So what the conjecture says is that this set behaves asymptotically as some positive constant b to the a of L log b to the b of L minus 1. Where a of L is the Fujita invariant of L in the Campana pair. So the infimum of real numbers T with the property that TL plus the canonical divisor of the toric variety plus the boundary divisor dm is effective. And B of L is the codimension of the minimal phase of the effective cone that contains the adjoint divisor A of L times L plus kx plus the boundary dm. So what this conjecture tells us is that we have a lot of arithmetic information about these points, but at the end of the story, all the arithmetic information is going to be contained in the leading constant of this asymptotic formula, and the rest is going to be determined by these two geometric invariants of the variety x, which where the, let's say, the parameter that defines the Campana condition, the mi's, they are all encoded in this special boundary divisor, which we wrote down. And so we also have a similar conjecture if we work over every number field. And still, the two exponents don't depend on the choice of the base field. So these are really just geometric invariants. All right. So what I wanted to do next is to give you some heuristical ideas of why this conjecture should be true. And then the result that we have. So this is what I call the hyperbola method heuristics. So the hyperbola method is one analytic number theory technique to count, well, lattice points. So what happens is that here we are looking at points as tuples of integers. So these are lattice points. they have some special condition like this, and they have to live in the region defined by this other condition here, which is certain monomials up to a given bound. Okay, so this condition in here is what I will call the condition that gives me the region of summation. So it defines some space with sort of hyperbolic shape where I want to count my lattice points. And this hyperbola method more or less works by covering the region of summation by boxes, because we know how to count points in boxes very easily, but we don't necessarily know how to count points in weirdly shaped domains like the ones defined by our height. Then we want to count points in each box. And this is something that we know how to do. And then we want to sum the contribution of all the boxes. Okay, so how does this work? Suppose that we have a box, and
why is it hyperbola?
Hyperbola because so for me, because it is used to count points in hyperbola-shaped regions. So perhaps I can give an example. So let me write down here an example. If x is P2, there's no hyperbola involved. The region of summation looks like, well, really just a box in A3. And there's nothing special going on in there. But if we go, for example, on P1 times P1, then the conditions where we want to count our points are something like xi, yj at most p. And now each of these conditions gives me something which looks like a hyperbola type of condition. Now this is just for the two chosen variables, and I have such things for each of the pairs of variables, and I have to intersect all of the conditions. So that's where the hyperbola term comes from for me. There are some other hyperbola methods mentioned in analytic number theory, of which I am not really an expert. But well, that term was coined by Blomer and Pruden, where they really were working on just products of projective spaces. And here the hyperbolic shape is obvious. And the main problem we have is that here this goes to infinity, this goes to infinity, this goes to infinity, and this goes to infinity. And we expect that at some point in these parts towards infinity, we have no lattice points to count if we remove all the points that lie in here. But understanding how to deal with that and precisely at what point one has to cut these tails, it is not obvious. And so, yeah, what the hyperbola method does is to say, okay, then let's just put boxes everywhere and count in boxes, and then figure out which boxes are going to give me the main term and which boxes are going to contribute so little. I have so little points they don't really contribute to the main term, so we're going to put them into the error term, and they have a negligible contribution. Does this answer your question?
Well, okay, to some extent, yes.
Okay. All right. All right, so to get an idea of how this works, we look at one box and see what happens. So we choose boxes so that each coordinate has a given size. Say BI. What does this mean? For example, we can take some box where yi has to live in something like bi up to 2bi. And we take the bi's that depend on the bound b that we want to set to, that we want to go to infinity. So something like b to the ti, where ti is a positive real number. So ti is going to be fixed for my box, and my box depends on b. So if we enlarge b, I will have a bigger box. And then if we have one such box, so I can try to understand the contribution of this box to the summation. So how many points are there in one such box? And well, I'm trying to count points, but not just. So if I were counting just integers there inside, I would have more or less up to some constant bi for each coordinate. But because I'm counting Campana points, so I'm counting points with these mi fullness conditions, then I have an exponent of 1 over mi for each bound. And this is because the number of integers at most b and such that z is m full. This is known to be asymptotic up to some explicit constant c, well, not the same as the c before. So let's say c prime and b to the 1 over m. And this is a result by Erdős and Zekers. A very old result. So each of the sides of the box is going to give me a bi to 1 over mi, and the whole box is going to give me a product of these. And this is the same as v to the sum of the ti over mi I from 1 to s, where I'm just substituting now this expression bi is b to the ti in this formula. So this gives me one possible exponent of b contributed by the given box of the given size for b to the ti. So now there are two things that one has to understand. First, when does the box live into the area of summation that we're interested in? When does the box satisfy the height condition? So we say that the box is admissible for this counting problem well, if we want the ti to be positive real numbers, and then we want that the box is inside the area of summation. So we want to have that the sum of this alpha I sigma ti is at most 1 for every sigma. Why do we want this? So this comes from the fact that we want that our b, our bound, say b1 up to bs, to the L of sigma is at most b the bound. Okay, now I think I'm using too many b's. I'm sorry about that. So we are asking that all the points satisfy the height condition. A certain monomial has a size at most b, and then I'm putting my bounds into this condition, and what I get is that this thing here, which is product over I of bi to this alpha I sigma, and I just substitute the b to the di for the bi, and so I get this alpha I sigma di. And this is now what gives me this condition. This exponent is the smallest exponent of b. And this has to be true for all the monomials that gives my height, and so for all sigma. Okay, so whatever this means, these two conditions are just conditions on real numbers di, and they give me a polytope, say P, in R to the S. And the other thing that we have is that we are going to have in our main term of the asymptotic formula only the boxes in the region of summation that give the highest possible contribution. All the rest is going to be in the error term. And how do we measure the highest possible contribution? The highest possible contribution is given by the highest possible exponent of the box contribution. So in order to compute this number, we have to maximize this function. So we want to understand what is the maximal value of the linear function sum I from 1 to s of ti over mi on boxes that are admissible, so on the polytope P. And this is a linear programming problem. And what I prove in joint work with the Maris Schindler is first that this linear programming problem is dual to the linear programming problem, which is in the definition of the Fujita invariant. So that is a minimization problem in the definition of A of L, the expected exponent of B in the asymptotic formula. And then by strong duality in linear programming, the two problems which are dual to each other have the same solution. A of L. So the hyperbola method heuristic tells me that what the hyperbola method predicts for an asymptotic formula just by counting is that indeed the main term has a shape some constant times b to the a of L, which is what was also in the conjecture. And then we may have some other factor log b to some power. And this power here, the hyperbola method tells us that k is the dimension of the phase of the polytope P, where we have been doing our linear programming problem, where the function that we want to maximize has indeed the maximal value. And this is always a phase of my polytope. And then by working out the toric geometry behind this, what we show is that actually this dimension K is equal to P of L minus 1. Now, I don't have time to give you the details about this. It is a very nice computation, but essentially what we are doing is writing down everything in terms of cones into the vector spaces in the space of divisors of my toric varieties, and working out all the conditions between the conditions for the boundary and the fact that L is a very ample divisor, and what does the height mean in geometric terms and so on. And we find these cones that are dual to each other, and then we can show that we have these kind of conditions. And then finally, last result, we also have a theorem besides these heuristics, still with the Damaris-Schindler. So we prove that the conjecture holds for what I write here, many toric varieties X, where many means up to some technical condition that we need for actually working out the hyperbola method as a theorem, not just a heuristic. And with a special choice of the ample line bundle to be the log anti-canonical line bundle that we're going to require to be ample for this theorem to hold. And if you're curious, in this case, what we have is that the Fujita invariant is 1, and that the other invariant B of L is the rank of the Picard group. In particular, this theorem proves the conjecture for X of Picard number bigger than the dimension. That's one of the cases that is covered by this theorem. All right. I think I should stop here.
Thank you. Just thank you, Marta.
Thank you.
Any questions? If not, I have a couple of questions. So first, so you say that you show that some dimension of some phase equals what you expect. But do you in fact show that, so you have like two phases of two polytopes. One phase of some polytope is defined as the phase where some function attains its minimum, and the other is defined is a phase of a toric polytope, which is defined in geometric terms, like where your divisor lands when you move it to the effective threshold.
Yeah. So
do you really show that these phases correspond to each other?
Yes, that's what I do.
So it's not just the dimension equal to each other, but it's
no, they're really dual to each other. I don't know if you want to see a small diagram that shows, I mean, it doesn't really show that, but this explains kind of the thing. So what I have is I have space of divisors, and I have the space of linear functions on these divisors on the other side, and these are dual to each other. And then inside it here, I have a map down to the Picard group, which just sends divisors to divisor classes. So, okay, this is a space of torus invariant divisors. Okay, we have this map in toric geometry. So on the other side, by duality, we're going to have a subspace, which I'm going to call H, which corresponds to the Picard group under duality. So what one can prove is that inside R of S, here we have my polytope, which is defined by the conditions that I wrote down before, which is the one where we want to maximize a certain linear function. And what I prove is that the phase where the maximum value is attained, because L is very ample, is going to be contained inside H. So inside H, we are going to have P intersected with H, obviously. And here inside, we're going to have our phase F. And what happens is that my phase F does not contain the origin of R to the S. It is some phase out far away from the origin. What I can do is take the cone generated by this phase. So we have all of these inclusions on this side. And so the other thing that we can prove is that this polytope is defined in a way which corresponds on the other side in here to the effective cone of X. And then under this duality, here inside, I have this face that defines B, so smallest face that defines the adjoint divisor. And what I show is that this one now is dual to this one cone here. And now this face here has dimension B of L by definition of B of L, and this one here has dimension K, and this one here, which is a cone, is dimension K plus 1. And this is how the dimensions match to each other. But what I really do is prove the duality under this first duality in here, and then in here, and so all the way down. And well, that's how the proof goes, just by checking that indeed the conditions on one side, it was very, very surprising for us because the Maris does a lot of this number theory stuff. And she was telling me, you know, the parabola method gives me this polytope. What is this polytope? And then I started looking into it, and this condition looked very similar to something that made sense in geometry. And I figured that indeed that they were these geometric things. And yeah, that was very, very nice to see.
Very good. And another question. So can you give more details about this many? So what kind of technical conditions do you need for a variety?
Oh,
just maybe a rough idea of what kind of conditions.
Yeah. So one condition that I need is that this face in here is not contained in any coordinate hyperplane. Meaning, I'm going to give you an example in here. So for the projective space, if I write down my polytope P, it's just going to be a cube. And the face where the maximal value of the function is going to be attained is going to be this one in here, which is just a point. And what the condition, the maximal phase is there, so the condition is satisfied, but the condition, the maximal phase is not containing any coordinate hyperplane. It means in particular, it cannot be, for example, this point or something like this or something like this. Of course, if I change my function, my linear function, I could make any of these phases become the maximal phase. So in principle, everything could be allowed. So that's one condition. It's not extremely restrictive, but that's the one that gives me the restriction that I choose this line bundle, because for this line bundle, I can assure that it is true. And also the ampleness condition together gives me that. And the technical condition is a little bit more complicated. It says that
this is not a condition purely about the variety, it's a condition about the variety and L and the line bundle L.
Yeah, it's a condition about the variety and L and the boundary divisor dm. Because for what I got, the variety is the variety. L defines the polytope, and dm, the boundary divisor, so the Campana condition, defines the linear function that I want to maximize. So all three are involved. And here I choose L depending on the Campana condition, so that at least this condition is satisfied if L is ample. But then the other condition is what happens if I have some polytope. So of course in this picture, this is the nicest picture possible, and we don't see any pathological behavior happening. But the other thing that we do is at some point in the argument, we have to slice our polytope with the coordinate hyperplanes. So we take some conditions like Ti is epsilon I for epsilon very small, but not 0. And then what happens when we have these and we take epsilon I that goes to 0? So we look at maximization of the same function, but now with these extra conditions, and we are working in lower dimensional polytopes. And what we ask is, how big is the dimension of the phase where the maximal value is obtained in these lower dimensional polytopes? And we want that the dimension of this phase is smaller than the dimension of the phase where the maximal value is obtained on the whole polytope, this F in here. So there are two things that can happen. The maximal value is the same value, and because then I'm slicing this phase, then the dimension is going to drop at least by 1, and then I'm happy. But it can also happen that the maximal value on these section polytopes is smaller than the maximal value on the whole polytope. And if it is really smaller, meaning say A of L minus some fixed epsilon, so smaller than something like this, then I'm going to be happy. But I don't want to have the possibility that when my epsilon I goes to 0, then the new value tends to the original value. This is going to break out the argument. So the condition is that there exists some epsilon such that either the value on a sliced polytope is smaller than this, or I know that the maximal phase where this value is obtained as dimension at most k minus 1, so smaller than the one for the main term. So this is the technical conditions that we have. It's really technical. It really has to do with how we do the counting.
And suppose that your toric variety has large Picard number. So, and suppose that you pick L so that it is roughly random in this Picard group, Picard lattice. Am I right that in this case, the technicalities are going to hold?
So if the Picard number is large enough, because in this condition, I'm going to slice not just by a hyperplane, I'm going to slice by choices of as many as I like of these. And so there are two cases where the thing is nice, and we have some condition where these two cases cover all cases if the Picard number is large enough, meaning the dimension of my polytope is very large. So the answer is yes, we do have that condition for arbitrary L in that case.
Okay, thank you. Are there any more questions? If no, let's thank Marta again. With many coincidences.
Yeah, thank you. Thank you.